Students, when k0 there, then psi is equal to 0. That implies array factor maximum occurs there. That is the third point you are writing in the note. In the note, actually, continuation, fourth point. Broad, BROAD, broadside array. Actually, what is the meaning of broadside array? If the maximum radiation is at 90 degrees angle to the antenna array axis, then that is called as broadside array. So here, if the maximum radiation, is, that means maximum radiation means, students, electric field should have maximum value. So if the maximum radiation, okay, I will write it there. If the maximum radiation is 90 degrees to the antenna array axis, then it is called as broad. Broad means breadth side, breadth or width side. So broadside array, it is defined like that. That means meaning is like this, students. For example, this is y axis, this is the z axis. Here antenna elements are there like this. Okay, antenna elements are there like this. Now 90 degrees to this, na, here 90 degrees to this, na. So here radiation pattern is like this, 90 degrees to this one, maximum electric field occurs. So electric field is maximum, which makes exactly 90 degrees to the array axis here. So here, na, it is 90 degrees like this, 90 degrees. Then it is called broadside array. That is the definition of that one. So that means here you know that electric field total is equal to E1 into array factor. Now I told you, if array factor is maximum, then total electric field is also maximum. Now electric field maximum required, at theta is equal to 90 for what do you say, broadside array. That means this is one point. Next point, electric required at 90, E maximum required at E theta 90 for broadside array. This is one point. Actually, electric field maximum is required at 90 degrees for broadside array. That is one requirement. Second requirement, array factor maximum. That means that happens when psi is equal to 0 is required for electric field maximum. That means if this is maximum, this is also maximum. Now the conclusion is that you know that psi is equal to beta d into cos theta plus alpha. So this is 0 required, 2 pi by lambda, then d cos of 90 plus alpha, cos 90 0, so alpha is equal to 0. The meaning is that if you take alpha 0 here, in this case I1 is equal to I0 at an angle of 0, then I2 is equal to I0 at an angle of 0, I3 is equal to I0 at an angle of 0. That means you take 0 0 0 phase shift, then automatically you get this type of pattern. That is the design. Actually it is called design. What is the meaning of design? Design means what should be the alpha value, that is called design. Alpha should be 0 for this. So, dear students, for final conclusion, for broadside array, mm, theta is 90, then array factor is equal to 0, then alpha should be 0. So, for broadside array. Now, actually, there are some formulas here. Half power beam width. These are for broadside array. Half power beam width is equal to, these are formulas, student, you have to remember them. Lambda by L, it is in radian actually. It is in radian. So, lambda by L, it is in radian, student. If you want degrees, na, that is equal to lambda by L, then 1 radian is nothing but 57.3 degrees. Now you get in degrees actually. Okay, you remember this one, lambda by L. So here, what is lambda? Where lambda is equal to V by F, that is C by root mu r epsilon r into frequency. If it is air medium, mu r 1 epsilon r1, so C by F only, that is. Next, coming to this, L is equal to N minus 1 into D, that is called array length, or otherwise length of array. Student, you know that na. For example, if 3 antennas are there na, only 3 antennas are there na, then length is equal to 2D. What is this length now? 2, 3 minus 1 into D actually. So if 3 antennas are there, 1, 2, 3 are there na, then this is D. So 2D is the length of the antenna array. So then that is equal to, in terms of N, that is 3 minus 1. So N minus 1D, like that, dear students. So here D is distance between antenna elements. N is actually number of antenna elements. Okay, students. Okay, right. So lambda by L, length by length, it is unitless actually, radian you get. You remember that one. Half power beam width for broadside array. Okay. Now, this FNBW, you know that na? FNBW is nothing but 2 times of half power beam width, student. 2 times of half power beam width you get. That no need to remember. Next, directivity of broadside array is equal to 2 times L by lambda. So you remember this one also. These formulas you remember, student. Just before examination you revise them. This one and this one you have to revise them. Okay. Length of array, L means, capital L means here. Next, in the note 5th point, end fire array. Actually here fire means radiation. Along the endings of the antenna array, maximum electric field is present. That is the meaning of end fire array. So here actually in end fire array, electric field maximum value occurs at the ending of the antenna array. Now case 1, student. Case 1. Actually, if this is the antenna array axis, this is Z axis, na? So now this is first antenna, second antenna, third antenna, fourth antenna. This is one end, this is other end actually. So you want maximum radiation in this direction, like this you want, then this is Z axis actually. So theta is equal to 0 here on the Z axis. You can increase this length. So if you want maximum radiation in this direction, then theta is equal to 0 on the Z axis. If you want maximum radiation down direction, no, downy, actually ends means the antenna array ending means this is one end top side, bottom side also one end actually. This side one end, bottom side one end. So if maximum electric field is required in this direction, then for this theta is equal to 0. Theta is equal to 0, student. Now you start doing design. So if you want maximum radiation in this direction, then you start design. So here for array factor maximum value, psi is equal to 0. Next, electric field maximum value, otherwise simply I will write E max. E max is required at theta is equal to 0 angle required. Now design means you calculate the alpha value. You calculate the alpha value. Then psi is equal to beta d cos theta plus alpha is general equation. Psi 0 required for array factor maximum. Then 2 pi by lambda into d. Then cos 0 plus alpha. Cos 0 is 1. So alpha is equal to minus 2 pi by lambda into d. So this is the formula actually. If d is equal to lambda by 8 for example, then alpha is equal to minus 2 pi by lambda into lambda by 8, then automatically you get lambda cancel, so you get minus pi by 4. The meaning is that first antenna current is equal to I naught at an angle of 0, you have to give. Second antenna current is equal to I naught at an angle of minus pi by 4, you have to give. Then third antenna current I3 is equal to I naught at an angle of 2 times of minus pi by 4 means minus pi by 2 you have to give. Like that you keep increasing currents and also you maintain D is equal to lambda by 8. So D is equal to lambda by 8 between the two antenna elements, lambda by 8, lambda by 8. So you take the current elements of I naught cos omega t, then second one I naught cos omega t minus pi by 4, then for third antenna I naught cos omega t minus pi by 2, then antenna element distance is lambda by 8, lambda by 8, lambda by 8. Then automatically your electric field radiation will be like this. Maximum value comes at theta is equal to 0. That is called design actually. So this is the design, student. This one you have to remember. For example, you can select D is equal to lambda by 6, then that is different value here, angle, like that it is. So here case 2, student, case 2 is like this it is required. So this is the, what do you say, y axis, this is the antenna array. So like this you want maximum electric field, na? So here maximum electric field is required. This is theta is equal to 0. Here theta is equal to 90 degrees. Here theta is equal to 180 degrees you want. So in this case this is the maximum electric field required. So now you want for array factor maximum value psi you need 0. Second one, here in this case, E maximum is required at theta is equal to pi. That means psi is equal to That means psi is equal to beta d cos theta plus alpha. So 0, 2 pi by lambda d, then cos pi plus alpha. From this cos pi is minus 1, so minus, so ultimately 2 pi by lambda into d you get, this is the alpha required. So example I will tell you, let d is equal to lambda by 8, then alpha is equal to 2 pi by lambda into lambda by 8, lambda cancel, and ultimately pi by 4 you get. Actually, what is the meaning of this, dear students? This first current element, I1 is equal to I naught at an angle of, so I naught at an angle of 0. Second current element, I naught at an angle of pi by 4. Third current element, I3 is equal to I naught at an angle of 2 pi by 4. Next 3 pi by 4. Like that you have to increase. Then you have to maintain this distance between the antenna elements as lambda by 8. So what you do, if any student want maximum electric field in the down direction, then that student has to take d is equal to lambda by 8, then automatically currents are given like this, then that student get this type of uh, yeah, radiation, maximum radiation in down direction. So that is the meaning of that. Now, dear students, so I will be writing some formulas of what do you say, half power beam width formulas na for this. I am writing them. You remember those formulas, dear students. You have to remember them. Okay, you remember those formulas. Just before examination, na, you just before exam, 2 days or 3 days, na, you remember them, right? Okay. So for end fire array, half power beam width is equal to root of 2 lambda by L. This is the formula you get in radian. Radian you remember. If you want in degrees, already I told you, you have to multiply with that angle. Okay. Then next, where L is equal to n minus 1d, same as previous one. Then Fn BW, na, first null beam width, na, that is 2 times of this one only, 2 times of half power beam width. So no need to remember that one. Now directivity. So directivity d is equal to here 4 times L by lambda. You have to remember this one, directivity d, or otherwise you can put this in brackets. Directivity d is equal to 4 L by lambda. So you have to remember this one, dear students. Okay. So dear students, now let us write one note, that is actually grating lobe. Grating lobe is identical to the main lobe, but in an undesired direction. We don't want this, that means we don't want grating lobe actually. Okay, so that is the meaning. So grating lobe is identical to the main lobe, but in an undesired direction. That means we don't want this one, but it is similar to main lobe. So that means lot of power will be wasted in this. Okay. For uniformly grating lobe occurs, here I am writing reason. Grating lobe occurs, grating lobe occurs in uniformly spaced arrays when distance between antenna elements is very high. Actually, now what happens now, student? If distance between antenna elements you make 2 lambda like that, then the antenna elements are far away, so that again they behave like single antennas. That group effect is lost. Whenever those antennas are very closer, that means at appropriate distance, then only all together behave and give the desired characteristics. So first of all, I wrote what is grating lobe. Grating lobe is identical to the main lobe, but in an undesired direction, that is not required. Then why grating lobe occurs? Grating lobe occurs in uniformly spaced arrays when distance between antenna elements is very high. So, for example I will tell you, broadside array. Broadside array. For example, if you take broadside array, the meaning of broadside array is, let us take this is antenna array axis, like this it is. So in broadside array, the radiation pattern required like this. Okay, it is symmetric. I will make. Okay, the radiation pattern required is like this, student. Now this is a desired, required, that is. This is also desired, but unfortunately you got one lobe like this. You got, but we don't want this one. But why you got this one? Because here distance d is maintained very high. Whenever you maintain distance very high, then you get this. This is similar to main lobe actually. So this is called grating lobe. So it is undesired lobe. This is because now for broadside array this is desired, but this is not desired, dear students. So undesired one, this one. Now it is observed that for broadside array, grating lobe occurs when d greater than or equal to lambda. Okay. Similarly, for end fire, it is observed that what they have done, they keep increasing the distance. Then whenever a distance was more greater than or equal to lambda, then they started getting these type of undesired lobes. Then they have decided this is the length. Similarly, for end fire array, grating lobe occurs when d greater than or equal to lambda by 2. So in an endfire array, grating lobe occurred whenever d greater than or equal to lambda by 2. Now commonly, how to avoid grating lobe effect in broadside? D should be less than lambda. How to avoid in endfire? D should be less than lambda by 2. Then how to avoid commonly? The both are called as linear uniform arrays. So how to avoid commonly for both of them? Then d should be less than lambda by 2. So for linear uniform arrays, that means meaning is broadside comma end fire arrays. They are both are linear arrays because distance uniform we are taking. Both are uniform arrays because same magnitude of current we are giving. So that is why for linear and uniform arrays means broadside as well as end fire, for both of them arrays, grating lobe can be eliminated, eliminated by taking d less than lambda by 2. That is why I took earlier an example d lambda by 8, lambda by 6, lambda by 4, like that you can take d less than lambda by 2 actually, less than lambda by 2. So this one is the common for both of them. If only asked for broad side, d less than lambda. Only asked for end fire, d less than lambda by 2. For both of them commonly asked, then once again d less than lambda by 2. If you maintain d less than lambda by 2, then that grating lobe can be eliminated, dear students. Okay. Now, let us talk of effective area of the antenna. It is sometimes called A effective or simply AE. AE or otherwise A effective. Effective antenna. My dear students, here let us say one antenna is there here. Okay. Here it has some radio here. Here some radio is there. Radio. That antenna is there for this antenna. Now here some EM wave is coming like this. EM wave is coming like this. So this EM wave has a average pointing vector whose unit is watt per meter square. This EM wave has. Now this antenna has a effective area. This antenna has effective area. Now I am giving hints for you. You think of it. Actually, power received by this antenna is measured in watts. Then this EM wave has average pointing vector, that is available power density near the antenna is watt per meter square. Then from that, how you get effective area? Power received by average pointing vector. So watt by watt per meter square gives actually effective area. My dear students, here discussion is like this. For example, this is radio and this is antenna of the radio. Then EM wave is coming like this. Then EM wave is received by this area. Only this side area EM wave is received. That is called effective area. But this side total physical area is present. But there is no use of this physical area. This is back side. So only front side area is receiving the EM wave. That is called effective area. So that is why physical area is always more than the effective area, student. So there is no use of physical area, but antenna has this side total area is there, but there is no use of that. Now whatever EM wave comes this side, that hits this side, and this area called effective area only receives the EM wave. So dear students, so here how you define the effective area of the antenna. So effective area is defined as the ratio of power received by the receiving antenna, RX antenna, otherwise received by the antenna, you write simply received by the antenna and available power density. That means nearby antenna how much power is available. That is nothing but average pointing vector. Unit is watt per meter square. So that means effective area is equal to power received divided by magnitude of average pointing vector. So already this is watt. This one is watt per meter square. So watt cancel, you get meter square, students. So this is the definition. Okay, in any question power received is given and the average pointing vector magnitude is given, then you can get what do you say, mm, effective area you get. If you want, you can write the unit of the AE outside, that is meter square, student, because you will be confused here. So meter square. So already I have written power received, this one, available power density or otherwise average pointing vector is this one. So after doing derivation, there is another formula is there for effective area. There are two formulas. One formula is when power received and average pointing vector is known, taking the ratio that gives the what do you say, effective area. Another formula is there, student. Here, second formula, effective area is equal to lambda square divided by 4 pi and directive gain. This is also another formula. So you have to remember this one also. This is also another formula, student. GD is directive gain. GD is a directive gain. This is second formula. For example, in this na AET na you put then lambda square by 4 pi GDT you have to put. So here AET is effective area of transmitting antenna, and now GDT is actually, okay, I will write directly one more thing here. AER means effective area of receiving antenna. Okay, next AE max means maximum effective area, like that. GDT means what do you say, directive gain. GD means directive gain of transmitting antenna. GDR means directive gain of receiving antenna. GD max is maximum directive gain, that is also called directivity D. Now after listening them, for example, in this formula, if you put AE R na effective area of the receiving antenna, then you have to put lambda square by 4 pi, then GDR. So AER meaning, GDR meaning I have written here. Similarly, in this, if you put AE max you want effective area maximum you want, then lambda square divided by 4 pi, then you have to take a maximum, what do you say, directive gain, that is nothing but directivity actually, this one, directivity. So no need to remember these formulas, you remember this one, that is more than enough. GD is directive gain here. Okay. So after this, we are going to discuss the free space equation. So actually, free space equation gives the relation between transmitting power and receiving power, gives the relation between transmitting power and receiving power by transmitting antenna, transmitting antenna and receiving antenna. Okay. So students, let us continue this derivation. First I will draw the diagram and I will explain these terms. For example, in the communication system, here you have transmitter that transmits the signal which is to be transmitted. For example, here let us say transmission line is there. So this is a transmission line. Okay. So here antenna is there like this. This antenna is there. So this is called transmitting antenna. Transmitting, I will write little bit bottom side because distance is to be written here. So this is a transmitting antenna, this one TX antenna it is called as. Similarly you have here distance I will reduce, student. Okay, like this. So this is called distance between them is R actually. In some books they write D also, small d also, doesn't matter. This is receiving antenna. Receiving antenna is there. Once again here transmission line is there. Here TX line is there. Then you have to supply the signal to the receiver. Let us say power supply to the receiver is PL, that is load actually. Power supply to the receiver or otherwise power supply to the load. Okay. Now here let us say this is transmitting antenna. It has it is transmitting PT power. It is transmitting PT power that is equal to P in into 1 minus gamma T square. I will tell you what is that. Then it has a effective area of transmitting antenna, directive gain of the transmitting antenna. So it has gamma T, reflection coefficient of the transmitting antenna. Similarly, PR means power received by this, and AER means receiver effective area, no need to write. GDR means receiving antenna directive gain. Already I wrote them. So what is this actually? I did not write. PT I wrote there. Power received by uh, RX receiver. RX means receiver antenna. RX antenna. Okay, that one. Now here gamma R is there. Gamma R means reflection coefficient at the receiving antenna. I will write that one. So now it is a free space here. Free space or otherwise medium is there. First, already you know formula. Once again, I am going to explain that here. For example, this is medium 1. This is medium 2. So here one EM wave is there. That means power in that is P in. Now some power is transmitted and again some power is reflected here. So power can either created nor destroyed. Total input power is equal to power. Total input power is equal to here power transmitted plus power reflected. Okay, this I am calling it as incident power. This is incident power. Now power transmitted is equal to incident power minus reflected power. That is nothing but incident power, you common 1 minus power reflected divided by P incident. So this is nothing but actually PTR. So this is nothing but P incident power into what do you say, 1 minus reflected power by incident power is reflection coefficient whole square, already we have seen. So that means power transmitted is equal to incident power multiplied with 1 minus reflection coefficient. That is what I have written. For example, here there is a transmission line. This is antenna. Antenna input impedance is load impedance to this transmission line. Then if they are not matched, transmission line. This is transmission line. Student, here this antenna has input impedance. The input impedance of antenna behaves like load impedance to this transmission line. If they are not matched, then reflection coefficient gamma t is there. Gamma t means ZL minus Z0 by ZL plus Z0. Z0 is characteristic impedance of this transmission line. ZL is nothing but input impedance of this antenna. If they are not matched, then gamma t value is present. If matching is done, then gamma t is equal to 0. Now if I supply P in power input or otherwise P incident, here I wrote P in means power input given to transmitting antenna. Then here reflection coefficient gamma t means reflection coefficient of receiving antenna. Their reflection coefficient is there. Because of that, some power is reflected, then some power is transmitted. Then how much power is transmitted? Total power transmitted by transmitting antenna, that is also called as power radiated. So total power radiated, so that is nothing but power transmitted is equal to incident power multiplied with 1 minus gamma square. But this gamma is to be taken for transmitting antenna here. So here everything is written. Now power transmitted by this antenna is this much. Again this antenna has directive gain. So in this direction power sent is PT into GDT, because this antenna is designed to radiate power in particular direction. Because the directive gain is a function of theta pi, the directive gain value will be more in this direction, because we want to send the power like this. So overall how much power sent here? PT power transmitted multiplied with directive gain and sent in this direction. Now near this antenna, what is the power density here? So here power density is there here near this power density. So that power density is equal to power density PD near the receiving antenna, near the receiving antenna is equal to power density is equal to how much total power it is sending? PT GDT divided by, here actually distance is r, it spreads spherically, so 4 pi r square. The unit of this is watt actually, gain no unit, so watt per meter square. This is nothing but magnitude of average pointing vector, this one. Of course this is nothing but magnitude of average pointing vector only. Now you multiply power density with effective area of the receiving antenna, then meter square gone, then you get power received by that receiving antenna. So power received by the receiving antenna is equal to power density multiplied with effective area of the receiving antenna. That implies power received is equal to power density is PT GDT divided by 4 pi r square. Then effective area of the receiving antenna will be written like this, students. I will write here. So formula, effective area of receiving antenna is equal to lambda square by 4 pi G D R. Actually effective area means lambda square by 4 pi into GD. For receiving antenna this one. For transmitting antenna, AET is equal to lambda square by 4 pi GDT. Generally GDT is equal to GDR, then both effective areas will be same. Okay, doesn't matter. Now effective area of receiving antenna is lambda square by 4 pi and GDR actually. GDR. Now students, this one PR is equal to, it is written like this now. Shall I write there? Okay. PR is equal to GDT, GDR, GDT, GDR, they are gains actually. GDT, GDR over. Now 4 pi into 4 pi square, lambda square bottom side, 4 pi r by lambda whole square. 4 pi r by lambda square into PT. So here received power by receiving antenna is equal to something into transmitted power by transmitting antenna. In that something, what are there? Beside this transmitting power, gains are there. They are good fellows. They increase that value, but this is bad fellow sitting in the denominator. So it reduces the received power value. So that is why that is called as path loss. PL. Path loss, that is called as. So this implies actually, this is the equation which you have to remember, dear students. So that is PR is equal to GD T GDR divided by path loss, that is called as path loss into PT. Okay. Now P loss, that means path loss, that is 4 pi r by lambda square, no unit distance by distance, that is called actually path loss. Okay, dear students, path loss, that is. Now if you want to represent this in decibels, no student, power received, actually that is single power, no. So that is why we have to represent maybe dBW, dBm, W like that, milliwatt like that. So dBW. Now GDT in decibels plus GDR in decibels minus path loss in decibels plus, because denominator is there means minus, then power transmitted in the dB watt, student. This is that one. So here if you want to remember, otherwise if you remember this now, that is more than enough, because in decibels numerator quantities added and this is subtracted like this. Here you have to understand one thing. If you represent power, transmitted power in dB watt, then received power is also in dB watt. This will be same. If you represent this dB MW, milliwatt, this is also decibel dB MW. If you represent this dB microwatt, this is also dB microwatt actually. Here GDT in decibels means that is 10 log 10 GD. Similarly, GD R in decibels means that is nothing but 10 log 10. This is GDT, then GD R. Similarly, path loss in dB means 10 log 10. Here path loss is nothing but 4 pi r by lambda square, students. 4 pi r by lambda square, that is the path loss. Next, power transmitted in dB watt, that means 10 log 10 power transmitted divided by 1 watt, that is the meaning, right? Similarly, power received in dB watt means 10 log 10 power received divided by 1 watt, that is. So here if you represent this in milliwatt, here 1 milliwatt, here also milliwatt, here also 1 million. Microwatt means here mu W comes, here 1 microwatt, here mu W comes 1 microwatt, but others will be same, dear students, right? Next, here this equation number 1, this equation gives power received by this antenna. Now how much power is transmitted into the receiver? Power transmitted is equal to power incident into power transmitted is equal to power incident into 1 minus reflection coefficient whole square. Here power transmitted into the receiver, that is called PL, into power transmitted is power transmitted is nothing but PL only, is equal to power incident is received power, because whatever power received, na, that is going to be incident into this receiver, then 1 minus gamma R square. So it is like this. Now power transmitted is equal to power incident 1 minus gamma square. So this is general formula. General formula. Now power supply to the load, that means power transmitted into the load, is equal to power incident to that is actually PR into 1 minus gamma of reflection coefficient whole square. This is the equation, power supplied. So where PL is power transmitted into the load. Why I am writing power transmitted into the load? Because to match with this formula, that means that PL is power delivered to the load actually. So PL is power transmitted into the load, or otherwise power delivered into the load. That one you can understand in that way. Next, PR. What is PR? Power is already I have written there. Power received by RX antenna. Power received by RX antenna. Gamma R means what? Gamma R means is reflection coefficient of RX antenna. So this is the discussion, my dear students. Now we have done this discussion. Whenever we have assumed, in this case we have assumed there is a polarization match. So these equations are derived by assuming polarization angle theta p is equal to 0. I will explain. Now you will not understand. We are going to describe that by taking theta p. Okay, don't worry about that. These equations are derived by assuming polarization angle theta p 0. Theta p 0. Now we have to talk of polarization loss factor. What is that? I will explain here. For example, dear students, here there is one receiving antenna like this. Now incoming EM wave electric field is vertical, then this receives a complete signal. There is no polarization mismatch. For example, receiving antenna electric field is in this direction. Incoming EM wave electric field is like this. Now this receiving antenna cannot receive the signal completely because electric field directions are mismatched. Electric field direction is called polarization. So there is a polarization mismatch. Then the polarization mismatch angle is called theta p. For example, receiving antenna electric field is like this, and incident EM wave electric field direction is like this. Then theta p is 0. Then mismatch angle is 0. Then there is a complete polarization matching. In this case, these formulas are valid. So whenever there is a mismatch between the polarizations of receiving and incident wave, then you have to multiply this PR, power received, with cos theta p whole square. That is called polarization loss factor. Students, because of polarization, how much loss is there? That is called polarization loss factor. So if you have to multiply this with the polarization loss factor. If there is a polarization mismatch, then power received is equal to this multiplied with the polarization loss factor. That polarization loss factor is defined as a polarization loss factor is defined as a this one unit vector of incoming wave electric field dot product unit vector of antenna electric field, then you take dot product, then you have to take whole square. For example, let us say this is the unit vector of incoming electric field, this is the unit vector of antenna electric field, then let us say angle between them is theta p, that is called polarization mismatch angle. Then this becomes actually modulus of ai modulus of aa, then dot product expansion, then angle between them is cos of theta p whole square. This is 1, this is 1, so cos square theta p you get. So for example, I will write this neatly, don't write, you are listening now. So students, now before polarization mismatch, before before if there is a polarization match, let us say power received is pr at theta p 0. Theta p 0 means cos 0 is 1. Then how much power is received whenever there is a mismatch? Then pr multiplied with this factor, polarization loss factor. So that is cos square theta p when theta p is not equal to 0. Then in this also you have to multiply power supplied to the load becomes pr dash, it becomes pr dash, students, right? I will be writing there. So dear students, now polarization loss factor, actually this is also called as polarization efficiency. In general, the polarization of receiving antenna will not be same as the polarization of the incoming that means incident wave. This is called polarization mismatch. Polarization mismatch. That means this is a receiving antenna. That electric field of the receiving antenna is like this, let us assume. Then if the electric field of the incoming antenna is like this, then there is a polarization mismatch. Then that angle theta is there, that is called theta p. P stands for polarization mismatch angle, theta p, that is. Okay. Now in this case, the amount of power extracted, that means this one received by the antenna from the incoming signal will not be maximum because of polarization loss. This loss is measured in terms of polarization loss factor, PLF. So because of polarization, how much value is lost, that is defined as a polarization loss factor. For example, this is the incoming EM wave. That incoming EM wave has electric field. Now let us say AI cap. A cap means unit vector, I means incoming or otherwise incident. So AI cap is unit vector in the direction of incident wave electric field, let us say, that is like this. Now AA cap means unit vector of receiving antenna electric field, that will be given in the question. So this receiving antenna electric field is like this, and incoming EM wave electric field unit vector is like this. Then angle between unit vectors of incoming electric field and antenna, receiving antenna electric field is theta p. So the theta p is called a polarization mismatch angle, or otherwise angle between AI cap and AA cap. So if theta p is equal to 0, then you say polarization is matched, then there is no loss. Then cos theta you define when theta 0, cos theta is 1, there is no loss. When theta not 0, then loss is present, then cos theta value less than 1. So that is why you can imagine that it should be multiplied with cos. How you get cos whenever two vectors are there? Take the dot product. That is the idea behind that. So polarization loss factor is defined as ai cap dot aa cap actually if you want to multiply for electric fields. But for powers you have to take whole square. So that is why taken square here. Then what is the expansion of that modulus of ai multiplied with modulus of aa, then cos of angle between them cos theta p whole square. So you get cos theta p whole square. No need to take here mod because already cos theta p whole square you take na, automatically that is what do you say, positive only. But why taken mod? The inside mod, if you do expansion of this, you get cos theta p. Then simply whole square is taken for that. So that is that one. Now if you want polarization loss factor in decibels, no students. So here, if you are not taking whole square, na, that is for electric fields. You are taking whole square means that is for powers actually. So if it is taken whole square, then for powers means 10 log you have to take. It is written in terms of unit vectors. It is written in terms of theta angle. It is written in terms of PLF. That means the polarization loss factor is given 30, 40. No. It is loss factor value is given. Then you have to take 10 log for to get the decibels. Now students, let the once again continuation to the this is actually continuation to this one continuation to Friis equation, because I wrote there Friis equation is solved by assuming theta p 0. Theta p 0 means then factor is equal to 1, there is no loss at all. That is the meaning. If factor is less than 1, that means there is a loss there. Okay. So let the power received by receiving antenna when polarization is matched, that means theta p 0 is PR. That's what we have derived. Then PR is equal to GDT, GDR divided by path loss into PT. Then power received by receiving antenna when polarization mismatch is present, then let us call that power as a PR dash. PR dash, that means power received by receiving antenna whenever there is a polarization mismatch is equal to power received whenever theta p is equal to 0. I wrote here. That is this one multiplied with polarization loss factor. So that is generally less than 1. If there is no polarization mismatch, then theta p is equal to 0, then that factor becomes 1. So this is the one. Now in this case, power supplied to the load of receiver is PL is equal to PR dash into 1 minus gamma r square. Now I am concluding student here. I am telling you, if power received whenever there is a polarization match, here PR is present. Simply that PR is present. But whenever there is a polarization mismatch, in place of PR you have to put PR dash. That PR dash is equal to power received when there is a polarization match multiplied with polarization loss factor. Okay students. Right students, you see the antenna chapter, first question, workbook question. So that is question number 1. Radiation pattern of antenna is given actually u theta pi, that is generally, but here it is a function of only theta. So cos power 4 theta for 0 less than or equal to theta less than or equal to pi by 2 it is given. So for only this equation is valid for this angle. You have to find directivity. So that is the formula. Now directivity is equal to 4 pi into maximum radiation intensity divided by total power radiated. Now at theta is equal to 0, then u maximum is cos 0 power 4, that is 1 actually, right? That is u maximum. It is very simple student. Whatever angle term is there, now beside 2 is there, 3 is there, they will be the maximum value. Okay. Now given radiation intensity, then power radiated is equal to double integral u theta pi solid angle differential solid angle, that is a double integral cos power 4 theta d omega is actually sin theta d theta d pi. Actually, these questions are very simple. You have to remember the formulas thoroughly, student. Right. Now, if you take sin theta as x, then sin theta, if you take cos theta as x actually, then differentiation is minus sin theta d theta will be dx. So you get first you separate them. Integral cos power 4 theta sin theta, theta term separately have done, integral d pi. So here pi varying from 0 to 2 pi and theta varying from 0 to pi by 2 has given 0 to pi by 2. So this is nothing but minus of x power 4 means cos power 5 theta divided by theta, no students, 5, then theta varying from 0 to pi by 2. This is pi varying from 0 to 2 pi. So I will write here, na, place is there. So that is equal to, this is a cos pi by 2 0 minus cos 0 is 1, minus in 1. So 1 by 5 you get. So this is 2 pi by 5 you get. So 2 pi 1 by 5 you got. Now directivity is equal to 4 pi into u maximum is 1, power radiated is 2 pi divided by 5. So 2 pi cancel. After cancellation, 2 pi cancel, 2 get 10 you get. Next, that fellow calculate in decibels. So directivity in decibels is equal to 10 log 10 d, that is equal to 10 log 10, you got 10 this one. So ultimately you get 10 dB. So that is the answer, option A. Okay. Next, question number 2. So in this question, it is given that half power beam width in one direction is given, half power beam width given, theta half power beam width in one plane 30 degrees is given. You write that into radian, that is 5 by 6 radian. Similarly, in other plane, theta half power beam width in second plane is given as 45 degrees, that is pi by 4 actually. Now directivity is asked 4 pi divided by theta half power beam width in one plane in radian. I told you, in theta half power beam width in second plane, that is perpendicular to the first plane, I was telling you while explaining the theory. So 4 pi divided by pi by 6 multiplied with pi by 4, pi cancel, you get 4 into 4 into 6, 1 pi cancel, this you get. Now you want in decibels, na student. So directivity in decibels is equal to 10 log 10 log 10 directivity, that is 4 into 4 into 6 divided by pi. If you calculate this one, this value comes 14.85 decibels you get, students. Okay, right. Next, third question. So third question is given as input power. Here given, actually here entire story is given in that question, but input power is actually 1 milliwatt. After giving a story, it is given as a lossless antenna. So given lossless antenna. Can you see the notebook, dear students? For lossless antenna, antenna, radiation efficiency, that is equal to power gain divided by directive gain definition, that is nothing but power radiated by power in is equal to 1 actually for lossless antenna. So power radiated is equal to power in. So how much power is radiated he is asking. Answer is 1 milliwatt only, student, because for that power radiated is equal to power input, because he himself, after giving so much story, he has confused. That's it. You have to catch the point, that is lossless antenna. Now question number 4. Here given power radiated is equal to 100 watts, he has given. Read the formulas carefully in the notebook so that you can solve all the questions. 100 watts. Now he is asking power radiated per unit solid angle. So power radiated per unit solid angle is nothing but total power radiated divided by total solid angle. Already I have derived, you see there, that is 4 pi actually. You get these many. This is 100 divided by 4 pi, that is equal to 7.96 you get. So the unit is power radiated is watt, and this is solid angle steradian. Watt per steradian is the answer. Okay. Now he is asking in that what is power density, dear students. So you know that power density is equal to PD is equal to total power radiated divided by 4 pi r square. 4 pi r square. Actually power density at r is equal to 10 kilometer distance from antenna is asked. So power density at r is equal to 10 kilometer distance from antenna he is asking is equal to that is equal to 100, this is power radiated, divided by 4 pi. Here r is 10 to the power 4 whole square, this one r is 10 power 4 whole square. Then you get a 0.08 micro watt you get. So I think option C is matching there. So that is the answer, right? Next, in next question, this is question number 5. So he is talking about radiation intensity and frequency relation, dear students. Radiation intensity and frequency relation. Okay. So radiation intensity is proportional to the actually power radiated. Okay. So you see like this, friends. Radiation intensity is equal to U. It is proportional to power radiated. That power radiated is proportional to the radiation resistance. That radiation resistance is proportional to the 1 by lambda square, that is proportional to the frequency square, dear students. Okay, you see the formulas. Actually this is the power radiated. This one is radiation resistance. So this one is radiation resistance. So lambda and frequency square. He has given actually, that means U2 by U1 is equal to F2 by F1 whole square. That means U2. So this is he was given frequency 2 is first frequency, half of the first frequency, so that is f2 is f by 2 divided by first frequency. If you take f, then second frequency has given f by 2 whole square. That means uh, into, okay, you take like this, then u1 is equal to, u2 is equal to, this is 1 by 4 multiplied with u1. So he is calling this first intensity as I, so that is I by 4 is the answer. He is calling u1 as I, so I by 4 is the answer. So that is equal to I by 4. Okay. Now this is question number 6. In this it is given as input power is equal to 40 pi watt and radiation efficiency in percentage is equal to 90%. That means radiation efficiency is equal to 0.9 actually if you remove the percentage. Next, here maximum radiation intensity is 150 watt per steradian is given, right? Then we know that power calculation, actually eta R is equal to radiation efficiency is equal to power radiated divided by input power. So if you want power radiated, that means radiation efficiency into input power. So input power is given here. So radiated power is equal to efficiency is 0.9 and input power is 40 pi, right? Now that is nothing but 36 pi watt actually, right? Now dear students, you can find directivity. Directivity is equal to 4 pi into maximum radiation intensity divided by power radiated. That is 4 pi into maximum radiation intensity is 150. So divided by this is 36 pi. Now this value becomes 16.67. 16.67. Actually, he has asked some print miss is there. The question is find the directivity or otherwise maximum directive gain. That same thing in decibels he has asked. That print miss is there. So if you want this in decibels, then 10 log 10 D is equal to this one 16.67. So that is equal to, you get 11.76 decibels you get, right? Option A is correct for this. Actually there is a print miss there, that he has asked a directive gain and also directive gain in decibels. That is the question actually, right? Now question number 7. In this question, student, for Hertzian dipole antenna, on which plane there is a circular shape radiation pattern? Already I told you this one. I was telling you to remember this XY plane. On the horizontal plane angle pi 0, there we have seen, I have drawn the picture like this. That was a circle on XY plane. XY plane is nothing but Z is equal to 0 plane, dear students. So for Hertzian dipole, for Hertzian dipole on the XY plane, or otherwise XY plane is nothing but Z is equal to 0 plane, that is XY plane or Z is equal to 0 plane. I was telling you, no, theta is equal to pi by 2 we have taken. Theta is equal to pi by 2 means if you see, actually this is y axis, this is x axis, 3D picture, this is z, theta is equal to 0 here, theta is equal to 90 for xy plane, this is x, this is y, for xy plane angle is 90 actually. So that is that one xy plane. Plane radiation pattern is circle shape. So radiation pattern, pattern means shape, radiation pattern is circle shape. So that is the answer. So option is C for that one. Okay. So students, this question number 8, given F is equal to 10 megahertz, students. So maximum electric field is given as 2 millivolt per meter, that is equal to 2 into 10 to the power minus 3 volt per meter, right? Then directive gain is equal to 1.5, and you know that lambda is equal to C by F, so that is 3 into 10 to the power 8 divided by 10 to the power 7, that is 30 actually. Now we know that effective area is equal to lambda square divided by 4 pi into directive gain, that is 30 square divided by 4 pi. Directive gain is 1.5, so actually 107429. So by definition, effective area, one formula was there, I told, no? Power received divided by average pointing vector, actually this one. So from this you can say power received is equal to effective area into average pointing vector, that is nothing but power received is equal to effective area. What is this, student? Here half into this electric field maximum square is given, no? What is average pointing vector? Half into electric field maximum square by eta naught. So here AE you got here, that is 107.429, then half into EM square, electric field maximum value is this one, 2 into 10 power minus 3 whole square divided by 120 pi, right dear students? Now if you calculate this value, you get 0.569 micro watt you get, right? So students, this is question number 9. It is given that a half wave dipole antenna, right? So for a half wave dipole antenna, we know that GD max is equal to maximum directive gain 1.64, right? Then it is given that power radiated, it is given in the question, it is given power radiated is equal to 10 cube watt is given, right? D is equal to 10 kilometer is given. Then he wanted RMS value. I have derived one formula. Did you remember? First you take actually, what do you say, maximum electric field, no student, that is 60 power radiated, then you say gain of the transmitting antenna root of divided by distance, actually this distance is R, at which distance you want. So RMS is required, na? Then RMS is nothing but EM by root 2, that implies ERMS is equal to 30 comes there. So 30 into what do you say, power radiated, then root of divided by R. So ERMS is equal to root of 30. Power radiated is actually 10 cube. Then GD is 1.64. Actually maximum we are calculating in the maximum directive gain direction, ERMS value you are calculating. So that means here R is 10 into 10 to the power 10 kilometer. Now this is equal to, you get 22.18 millivolt per meter you get, right? So millivolt per meter in the direction of maximum radiation, right? So option is D for that. Now let us solve question number 10. So question number 10. For half wave dipole antenna, he is talking of 4 half wave dipole antennas are there. Anyway, we know that for half wave dipole antenna, radiation resistance is 73 ohm, and for single, actually for single half wave dipole antenna, for single half wave dipole antenna, power radiated is equal to half into Im square into radiation resistance. Actually, he is saying 4 half wave dipole antennas are there in that. So that means for 4 half wave dipole, for 4 half wave dipoles, power radiated is equal to 4 times of this one. So 4 times of half Im square. Actually, for single half wave dipole antenna, this much. For 4 dipole antenna means 4 times you have to multiply. So that is nothing but 4 times and 1 by 2. And here Im is given as 0.5. Actually, in the question it is given 0.5. Half into Im is 0.5 it is given. Then radiation resistance not given, but we know that radiation resistance is 73. So Im is given as 0.5. You get 36.5 watt you get. So that is the answer, students. Now the question number 11. Question number 11. So in first case, L is equal to 1.5 meter given, then frequency is 100 megahertz. First, if frequency is given, length is given here for this antenna, frequency is given. First, you find lambda, that is C by F. 3 into 10 to the power 8 divided by F is 10 to the power 8. So that is 3 meter. Now take the ratio L by lambda. So L is 1.5. This is 3. Now that implies L is equal to lambda by 2. You get this is equation number 1 for first case. And for second case, length of the antenna is 15 meter is given. Frequency is actually 10 megahertz is given. So from this information you find lambda, that is C by F. C is 3 into 10 to the power 8. F is 10 into 10 power 6 is 10 power 7. So lambda you get 30 meter actually. Now for this you calculate L by lambda. 15 by 30, that implies L is equal to lambda by 2 once again. So this first antenna length 1.5 operating at this frequency, second antenna length is 15 meter operating at this frequency. But again, if you calculate length in terms of wavelength, for both antennas the same wavelength, so both of them have same radiation resistance, so that is why both of them radiate same power actually. So right, students, so here both antennas from equation 1 comma 2, as both are lambda by 2 antennas, both are lambda by 2 antennas, so they radiate same power because radiation resistance is same for both of them. So that's why you can say answer is B in that. Okay. Answer is B. Now you see the question number 12. Question number 12 actually given, dear students, lambda is equal to 492 meter, right? Given antenna height, is equal to, that is nothing but length, that is actually it is given 124 meter. So you take L by lambda ratio, no student. L is 492, this is 124. Approximately this is lambda by 4 antenna, approximately, that is more than enough. So for lambda by 4 antenna, radiation resistance for lambda by 4 antenna, radiation resistance of lambda by 4 is equal to radiation resistance of lambda by 2 antenna divided by 2. That is nothing but radiation resistance of lambda by 2 is 73 divided by 2. So that is 36.5 ohm you get, right students? Next, question number 13. For lambda by 8 antenna, he has given, for lambda by 8 antenna, it is given RL is equal to 1.5 ohm, student. Now we have to find radiation efficiency. So a lambda by 8 is nothing but lambda by 2 divided by 4, my dear students. That means radiation resistance of lambda by 8 antenna is equal to radiation resistance of lambda by 2 antenna divided by 4. That means that is equal to 73 by 4. So this value becomes 18.25 ohm, dear students, right? Now radiation efficiency in percentage is equal to radiation resistance divided by radiation resistance plus loss resistance into 100%. So radiation resistance is 18.25 divided by 18.25 plus loss resistance is given there 1.5 into 100. So the percentage you get is this one, approximately 89, dear students, 89% you get, right? So 89%, that is the answer. Because loss resistance is given, lambda by 8 antenna is saying lambda by 8 in terms of lambda by 2 is lambda by 2 divided by 4. That means then radiation resistance of lambda by 8 is radiation resistance of lambda by 2 divided by 4. You found this one, right? Next, question number 14. So a mast antenna of height, so this is a mast antenna. Actually mast antenna means there is a support for that, that is the meaning, right? To hang that here, to erect that, support is required. He is saying 50 meter, that is called length of antenna. Then given frequency is given as 600 kilohertz is given, dear students. Now let us find wavelength, that is 3 into 10 to the power 8 divided by 600 into 10 cube. So this value you get 500 meter, dear students. Now take the ratio of length and lambda. Length is given as 50 and lambda is 500, so that L is equal to lambda by 10 you get. Okay, so basically 62. So basically, dear student, I was telling you, if length less than or equal to lambda by 10, then radiation resistance is 80 pi square dl by lambda whole square if current is uniform distribution. But here current uniform distribution question that is not mentioned, then you have to take uh, 50 20 pi square dl by lambda whole square, because in Balani's book it is given. Actually, for these lengths now I wrote in the uh, notebook also, lambda by 50 less than L less than or equal to lambda by 10. For this range of lengths, then even if you give sinusoidal distribution, then automatically that becomes to triangle distribution. That is why 20 is taken. But I already told you lambda by 10 is coming. In the question it is given uniform current distribution, then definitely you have to take 80 only, 80 pi square you have to take. And also one thing, this matched antenna near the perfect conductor actually, so perfect conductor. And now what happens, dear students? But again, it effectively, length may be doubled, but effectively it radiates again into the upper hemisphere. So that is why no need to consider that effect. So here, now radiation resistance is taken as 20 pi square uh, dl by lambda whole square, otherwise L by lambda whole square. So here 20 pi square, here you can see length by, this is nothing but actually 20 pi square. If you take length as dl, then dl by lambda. If you take length as L, then L by lambda whole square. So this L by lambda is for this 1 by 10 only. So 1 by 10 whole square. This value is actually pi square by 5 ohm. So this is the answer, right? In the next question, question number 15, that is question number 15, it is given L is equal to 1 meter length. Actually, no students, in the questions currents are given, means they are maximum currents only. So maximum current is 1 ampere is given. Then F is equal to 10 megahertz is given. From this you can find length of the antenna in terms of wavelengths. So if you find that, for that you have to find lambda. So lambda is equal to C by F, that is 3 into 10 to the power 8 divided by F is given as 10 into 10 power 6 means 10 power 7. So that is 30 meter. You take the ratio na, L by lambda na, length is given 1 meter. So this is 30 you got so ultimately this one is length is lambda by 30 antenna. But you should understand here also you got lambda by 30. This is in between lambda by 50 and less than L less than or equal to lambda by 10. It is in this range actually. This is in this range only, lambda by 30. But here also that fellow did not mention, that is uniform current, he did not mention. Whenever uniform current is not mentioned, then you have to take for this range 20 pi square only. It is assumed that triangular distribution. In next question, that fellow gave lambda by 20, but particularly mentioned the current is there for, having uniform distribution he has mentioned. If uniform distribution is mentioned, for L is less than or equal to lambda by 10. If it is uniform distribution mentioned, there is no argument that you have to take 80 pi square. 80 pi square dl by lambda if it is uniform distribution. But if uniform distribution not mentioned, then it is assumed that that is a triangular distribution. Then you have to take 20 pi square. 20 pi square. Then radiation resistance of this is actually, so you take 20 pi square L by lambda whole square, that means 20 pi square. So L by lambda is 1 by 30 whole square here. So this value you get 0.219 ohm. Now you want power radiated in this question, that is half into maximum value square into radiation resistance, then half into maximum value of current. Actually current is given 1 ampere. In antennas that current is taken as maximum current, that is standard student. So 1 square then radiation resistance is 0.219. So Then answer is 0.1096. Option A. He himself asked find the approximate radiated power. So that is approximately answer A. It is answer A, student. Right. It is in option A. Okay. So students, question number 16. So given L is equal to 5 meter at frequency is equal to 3 megahertz. Okay. So lambda is equal to C by F you take, then 3 into 10 to the power 8 divided by F is 3 into 10 to the power 6. Actually that is 100 meter, dear students. Now L by lambda that is 5 divided by 100. This is 5 meter given lambda. So ultimately L is equal to, you get lambda by 20. Lambda by 20 you get. But in this question it is given uniform current distribution. So it is given uniform current distribution. It is mentioned particularly in this question, student. It mentioned this uniform current distribution. So whenever uniform current distribution is given, then for length of the antenna less than or equal to lambda by 10, you have to take 80 pi square for radiation resistance. So radiation resistance is 80 pi square, then L by lambda whole square, that is equal to 80 pi square. L by lambda is actually L by lambda 1 by 20 whole square. Now this value is actually 2 ohms. Okay. Now next question number 17. It is a standard question. Already I told you, for triangular distribution, current element having I of Z is equal to I naught 1 minus 2 mod Z by L. Radiation resistance is actually 20 pi square. This one 20 pi square L by lambda whole square. So this answer is D for this question. Okay. Now question number 18. So in this question, it is given that power received is equal to minus 30 dB. M means decibels compared with milliwatt actually. So for PT is equal to 1 watt power transmitted, right? Now first of all I will do this calculation. Power received in dBm, the definition is actually 10 log 10 power received divided by 1 milliwatt. So that is the definition of this. Now it is given what actually power received in dBm minus 30 it is given, that is 10 log 10. So power received divided by 1 milliwatt. So power received by 1 milliwatt is equal to cancellation. You get 10 cancel 10 power minus 3. So from this power received is equal to 10 power minus 3 into 1 milliwatt. So 1 milliwatt, that is 10 power minus 6 watt actually. Okay, this is power received. Now Frisch equation, power received is equal to transmitted power, otherwise GDT into GDR, gains are same then gain square, transmitted power divided by 4 pi d by lambda whole square. The distance is nothing but radius or otherwise R. I told you in some books they take R, some books they take capital R also, some book they take D also. I have taken a small r actually. So 4 pi r whole square. Okay. This is the Frisch equation. Now lambda na, lambda is equal to c by f you take, so 3 into 10 to the power 8, okay. Here frequency is given as actually 10 power 9. Frequency is given 10 power 9. So that's why you get 0.3 this one, right? Frequency is given 1 gigahertz student. So that is 10 to the power 9. Now from this you want gain. So you can substitute here. You can substitute here. This is 10 to the power minus 6 gain square into 1 transmitted power is given as 1 watt here. Then 4 pi r, 4 into pi into distance is given as 30 into 10 cube student. That means 30 kilometer is given. Divided by lambda we got 0.3 here whole square. From this you get g is equal to 400 pi. 400 pi, that is the answer, right? Okay. Now here next question is question number 19. Okay. In the question number 19, the given information is okay. So it is given power transmitted is equal to 10 watt is given. Okay. But if you want this in decibels, because others are given in decibels, power transmitted in decibel is equal to power transmitted in decibel, dB watt we are finding. So 10 log 10 power transmitted by 1 watt, that is nothing but 10 log 10 power transmitted is 10 here, divide by 1. So this is 1, you get 10 dB you get. Okay. Of course 10 dB watt you have to put, right? Then directive gain of the transmitting antenna is 10 dB is given. Then path loss in decibels given 100 dB is given. Okay. So circular polarization is given, student. Circular. Actually, the EM wave, incident EM wave is circular polarization is given. Circular polarization is nothing but already you know that half vertical plus half horizontal. Half horizontal. I told you, no, in circular polarization, x component is there, y component is there, then EA is equal to EB, then both are equal. So that is why circular polarization is equal to half of vertical plus half of horizontal polarization. So receiving antenna, actually incoming signal is circular polarization. Every circular polarized wave has a half vertical component, half horizontal component, like x square plus y square is equal to a square. X is horizontal, y is vertical, like that you take. Now receiving antenna is given vertical polarization. If receiving antenna has vertical polarization and incoming signal circular polarization, then receiving antenna has vertical polarization, only it receives half of the power actually. If P in is the power, then power received is equal to half of the P in. Okay. In that way, you have to calculate gain of the receiving antenna, you can calculate. So, okay. Given receiving antenna RX, I will write RX antenna is vertical is vertical polarized. So power received is equal to input power divided by 2. For circular polarization, we assume power is P in, then half of that only is received by this receiving antenna. Then what is the gain of the receiving antenna, dear students? So gain of RX antenna is nothing but GDR is equal to power received divided by P in. So power received divided by P in is equal to half. That if you find in directive gain of the receiving antenna in decibel, then you get 10 log 10 GDR, that is half. You get minus 3 dB, that is. Now all are in decibel, student. So if you substitute all are in decibels, then already I have written power received in dB watt is equal to, you know that, power GDT in decibel, GDR in decibel, minus path loss in decibel, power transmitted in dB watt actually. So what this fellow wants, power received in dB watt is required. Now substitute this is 10 and here, okay. So ultimately you get 10 minus 3 minus 100. In the sequence I am not substituting. So ultimately you get minus 83 dB watt. So that is the answer, dear students. Okay.